Day 20. All right, let's get in and see what day 20 is like. Grove Positioning System, GPS, encrypted files, something about mixing, encrypted files, a list of numbers to mix the file, move each number forward or backward in the file, a number of positions equal to the value of the number being moved. The list is circular, so moving a number off one end of the list wraps back around to the other, as if the ends were connected. For example, to move the 1 in a sequence like this, the 1 moves 1 position forward. To move the -2 in a sequence, the -2 moves 2 positions backwards, wrapping around. The numbers should be moved in the order they originally appear in the encrypted file. Numbers moving around during the mixing process do not change the order in which the numbers are moved. Okay, so we've got a ring buffer with items that have inherent IDs as well as a value that don't change when we move their position. So the index of them in the ring buffer cannot be their ID. And it looks like we get just the order from the initial set of numbers, and then we just have to move them around in order. We have to find the 1,000th, 2,000th, and 3,000th numbers after the value 0. What? So it's a cycle, but it's not. Okay, so we get to the end, whatever that is, and then we turn it into a cycle to get the 1,000th number. Mixing the file once, I think, is going through each number once. So we do 1, 2, 3, or -3, 3, -2, 0, 4, 2, -3, 3, -2, 0, 4. So mixing it once is every number up to 4. So if we have the number 4 here, we go 1, 2, 3, 4. So it's a mod for where it goes. Do we ever have a number that's larger than the list? It looks like we are going to, at least, unless we have 10,000 numbers in this list, which we might have. So I'm going to drop our input into here. Yes. So that very easily confirms that we have 5,000 numbers. And we have numbers like 6,000 here. So not all of our numbers are going to move within one cycle. So that's a big question, right? Like, we don't have any numbers here that have to move all the way around. So if we have like the 4 here, let's call it like a 10, right? If it's before 1, right, then it's 1, 2, 3, 4, 5. And then do you count this? Is this 6 or is this 6? Because we're moving the 4 and we can't move it like through itself if it's moving, right? But the starting position only makes sense if there are 7 numbers in here, right? So that's my big question. I think we can write the code for the first part first, but I assume the second part will, or actually even the first part, puzzle input, will bring that problem up. So our test input is this list. This is, luckily for us, a very easy parse job, separated list of numbers. The answer is 3. Okay. So let's just get started with parsing the input. I'm just going to write it as a separate function because I find that easier for me to deal with, and it makes more sense to share that code between part 1 and part 2 anyway. Call it a vec of I32s, and then it's just going to be a separated list 1, line ending, complete I32 with the input. Then we unwrap it, so we get the numbers. We debug this because that's the easiest way to figure it out. Test fails, 1, 2, -3, 3, -2, 0, 1, 2, -3, 3, -2, 0, 4. Okay, so we're good. That's our parsing done. Easiest parsing job since day 2. Let's keep that test going. All of this nom stuff is gonna get removed. I'm gonna use Rust Analyzer to just remove the unused imports, which cuts everything out. So we've got a vec here, right? And we need to iterate through every number at least once. Each of the numbers has like an ID associated with it. So I think that we need to do that somehow. I'm trying to figure out what the right data structure to put this in is. Because we could use a vec, right? And we could just move it, I guess. So we've got a vec and we've got a vec deck. I don't think the vec deck gets us anything that would be like useful that we don't actually get by having a vec. So in vec, we have bunch of functions. I'm just looking through to see what the most relevant one is. I feel like there's remove. So it removes and returns the element at position index within the vector, shifting all elements after it to the left. So this is basically what we're doing when we pluck out that first value. It does mean that all like 5,000 or up to 5,000 elements that could be to the right will get shifted over. We do need the order preserved, so we can't use swap remove. So if we find the element index that we care about, then we can use that index to remove it and then put it back in, which I think we can do with a mod operation. I'm just trying to think about how that would work. I do think that we need more than just number here. All right, so we've got, I think remove is the thing we need. And then we can find. I feel like it would be nice to have a different data structure here so that we're not just like actually moving these things around. I feel like there's something we could do that's a little bit more advanced that maybe is like grow the IDs. So like have the IDs for each of the numbers, and then do something that's a little bit more almost vector clocky, where we would have some kind of ID or more CRDT, where we would have some kind of ID and then that ID can get extended. So like if we have the IDs 0 through 9, then the ID for something that is between 1 and 2 would be like 1.1, for example. If we needed something between 1 and 1.1, we could do like 1.01 or something. I think using the vec is the simplest solution, and I think it'll probably work for part 1, so we should just do that, since I cannot think of a better solution offhand. I do think that we want numbers to have the IDs associated with them. So let's do, actually, as I start to say that, is there a way that we can get that index from parsing? That would be cool. I don't see anything offhand that would just be drop in. They're all binary number parsers. There is iterator support in NOM, which is interesting. So in this example, we have data, which is a string, and we have a terminated alpha1 pipe. So a set of alpha characters that ends in a pipe, and we've got data here. So we use iterator on the outside of that instead of like a separated list, which gives us an iterator that we can then use, basically. So that might work for us. Of course, we can just map over this. I'm just interested in showing alternative ways to do this. So if we take the exact same approach, right, where this is an iterator data terminated alpha1, and this is going to be line ending because that's our terminator, and we need complete I32 here. Iterator doesn't seem to have the same error handling. So we're building up a parser iterator. We're not building up like a parser. So let mute it equals this iterator. We need to bring this iterator in, nom combinator iterator. Terminated needs to come in as well. We have an issue with the return type, which is of course going to happen until we fix that. So I'll throw a to do in there to fix it. I think that this is going to be a return type problem here. So this is our input. So we don't have to pass input here. We pass input there. Complete I32 doesn't have the ability to infer the error, which is interesting. I assume that's why this is typed as iResult. So if we take that similar structure out here, we do parse equals it dot enumerate, right? Because that'll give us the index that it starts at. And then actually, that's all we need. So as long as we can remember that we have the tuple here, then we're good, because we don't actually need to map over it. We just need to collect into a vec. It.finish is a little interesting. Finish is a function on the parser iterator that we're getting back from that iterator function. And it says returns the remaining input if parsing was successful, or the error if we encountered an error. So that finish returns the value that we're not looking for. Let's do input and we don't care about the rest, right? Because this is numbers now, which means that we have to return okay input numbers to get this to work, which is interesting because that's going to be an okay value. So we'll do the question mark maybe. Does that work? I think it.finish iResult __. This is going to be a tuple of, I think, usize and I32 is the right thing. If we do the question mark handling there, do we need to write iResult? We do not, because we defined the iResult here, and question mark is returning the error into this. So iResult holds that error type. It.finish finishes the iterator, and then we have input numbers with our tuple. So now we have each of the indexes, or IDs is the way that I'm going to refer to them, as well as the individual numbers. The index is a usize, so we get to just loop over that, I think. I think we want to keep it as a number, but that's the way that this iterator works. It basically allows you to use a parser and consume that data as an iterator, and then do whatever you want to do to each value as it comes in from this parser, and then let NOM know when you're finished, and it'll handle the error for you if it fails, and you can return whatever you want. You can return the okay, or you can do whatever. So maybe not the most interesting way to do this, or rather, we could have just mapped over it here and enumerated and recollected, but it does save us that allocation, at least the first vec, And it's another way to do it. So maybe more useful if you are trying to use this as a combinator with a bunch of other parsers, because we are not using this value. So if we fail to do some processing in our iterator, it doesn't matter, right? But now if we wanted to, we could use numbers as just a regular parser combinator in some other input. So maybe more in a complex situation where we're parsing more complicated things, this would be more useful. So we've got our vec, we've got our IDs. I feel like we do need a second one anyway. Like we need the let state equals numbers dot clone kind of thing. So state is going to be the same thing as numbers to start off with, but we are going to do numbers dot iter. Either way, we have to mutate state. So we could do for number and numbers dot iter like this, and we could do mute state, and we could do the pop and whatever in here. Very classic for loop. So this is going to be ID and value. I don't think we use value here, so I'm going to leave it with an underscore. So we need to do state.find, I'll call it state value. State value.id equals ID. Then we can panic here. We do need to iter over this. What do we get here? We get double reference to the usize. So, oh right, no value ID. That's the problem. And then we get the reference issue. So we get state value dot zero, which is the ID, equals the pointer to the ID. In this case, we're doing a find. We get the actual value here. So I think we want like a find index. I think find index is a thing. So we could say find. We could enumerate and then do the find. I feel like there's supposed to be an index in here. Position. Position is what we want. We don't want find index. Why is Rust Analyzer not happy with me is a question I have at the moment. What did I do, Rust Analyzer? I don't know why Rust Analyzer is broken, or the formatter anyway. Oh, probably because I did this in panic. Well, that is a new one. I'm not sure. Let's try this. Cargo plus nightly format. And it's failing on something. I don't know what it's failing on. Maybe it's let else. Maybe let else is too new. That would be weird though. It was let else. Interesting. Okay, so for some reason, my version of Rust Analyzer is not having fun with let else. So I just put in if let as a stand-in for a second. That's super interesting, actually. Let else is very recent syntax, so maybe I just don't have a more recent enough install. Entirely possible. Okay, so let some index equals this. Let else allows us to stay at the root instead of nesting, so we get state.remove index. So let current equals state.remove index, and that gives us the actual value that we need to like reinsert. I'm curious to know which value we're supposed to mod this on. So if we do like index plus current dot one, right, that will give us how far to move it, whether it's positive or negative. But this needs to be modded by like state.length to give us an actual index to put it back into. And I think that's state.length plus one. At least that's my first guess. So new index would be this. Index and current dot one are not, let's get our watch back up. Index and current dot one are not the same numeric type. I think current dot one is an I32. So we actually do need to do the math as signed integers. So instead of turning current dot one into a usize, I'm going to turn index into an I32, which is fine for us, except that this whole thing is going to be negative. I don't offhand remember how negatives are treated in mod, so maybe we go check that first. Maybe we set up tracing today. That would be fun too. New index, current equals state.remove index. The new index is that index. Then we need to do state.insert new index current as usize. So the math here is something that I'm still, yeah, there we go. Insertion index is way too low when it should be that. So like if we absolute value that first, does that give us the right number? I don't know. This negative number, I feel like this absolute value is going to be like the length of the state minus it. That sounds more like the thing to do, but let's find out. So at the end of all of this, we need to take state, we need to iterate over it, we need to turn it into a cycle, and then we need what? 1,000th number, 2,000th number, 3,000th number. So if we have a cycle here, if you're aware of iterators in Rust, if we do a cycle here and we try to get the 1,000th number, then we need to call next on that iterator every single time because iterators can have effects. So we can't auto optimize it to just skipping, even though we could do something like, what is it, .nth, and we do like 1,000th, right? So maybe we'll do some profiling too. That would be fun. So let's do let mute it for iterator. We're going to cycle the iterator. A is the 1,000th value, And then we do a plus b plus c dot toString is supposed to be our answer. So this should be wrong, right? Each of these will be unwrapped because it always needs to succeed. And then we'll do dot one because we don't need the indexes. Left is -3, right is 3. That's interesting. So if we debug a, b, c equals -3, those numbers are clearly wrong. The question is, why are they wrong? So we've got a, b, c here, -3, 2, and -2. Those are probably the wrong numbers, right? So 4, -3, and 2. So those are all wrong. So because we're going to get into logging stuff out here and then wanting to get rid of it, I think I'm going to bring in tracing. So cargo add tracing and tracing subscriber. So tracing and tracing subscriber. Of course, it's cargo and not carg. So what is tracing in Rust? Tracing in Rust is what you can think of if you're not familiar with the idea of tracing as a logging framework. So it can act almost exactly as the logging frameworks that you're probably used to with different levels and things like that. But under the hood, it functions on this idea of spans. So from a user perspective, the idea is that you use like this macro, for example, to create a span before this function runs and close it after this function ends. And anything that you log out as an event inside of this function gets attributed to that span. So in this way, you create this giant tree of basically context, right? From the top level function that called the next function, that called the next function, that called your function. And it lets you keep all of that information around, or as much of that information as you want to keep around. Under the usage that we're going to see today, we aren't going to see a lot of that extra information or extra context because we're going to be using it much like this, where it's just an event at like an info level that prints out some string and some value. But in a distributed tracing context, on a running web server, for example, you can keep all of that span information, keep the distributed trace ID along with it, and then send that to some open tracing or honeycomb kind of thing to actually go query all of the things that are happening inside of your distributed system, which is really cool. So it goes all the way from like very basic, I'm going to log out a string, all the way up to distributed tracing across multiple microservices. And of course, if you don't know, this is a project under the Tokyo async runtime project. And we're going to go to the tracing subscriber crate, which is one of the tracing crates. We're going to go into the format submodule, and this is how we're going to set up tracing today. So we need to use tracing subscriber, and then in our like main function, basically, we're going to need to set up tracing. For our usage, I'm going to set it up in part 1 and part 2. So tracing subscriber format init for part 1 and tracing subscriber format init for part 2. And this is like just setting up something that will work for us. So now as that recompiles, I'm going to do tracing or use tracing star because I think that brings in all of the like easy to use macros. And I just realized I left the bevy dependency in here, which is a pretty heavy dependency. So I'm going to get rid of that real quick. So for example, we have source lib.rs40, right? And if I change this from debug to info, which is one of the options, we see that nothing is really printing out anymore. So we expected to see ABC, but we don't see it, even though we do have tracing subscriber format init set up in main. And the reason for that is that we still have to set it up in our test if we want it. And now you can see the info logs coming out. So if we want this to be log information that comes out from our tests, which in our case, I think we do because we are running tests pretty often. When we run our functions, right, all we get is day 20, ABC, A equals 3, B equals 2, C equals -2. This is, I actually really like this output. It gives us a timestamp, it gives us the log level, gives us the crate that it occurred in, or the crate that the log is coming from. It gives us the string that we passed in, as well as the values that we passed in. But wait, there's more. For only 3 easy payments of $19.95. I haven't seen an infomercial in so long. So if I take this instrument and we put this on process part 1, we see right now that it says day 20, which is the crate that the log's coming from, and then our output here, which is the 3 values that we're passing in. Notice that we aren't setting them up to be distributed as or logged out as A equals whatever, but that we just get that for free. Also notice I'm using the info shorthand here. I could also use warn or debug or whatever. As soon as I save this, this test is going to rerun, and it's going to include the context from the process part 1 function in that log output. And this is a very simple example, right? This process part 1 function takes a number of arguments. Input is one of the arguments. So if you read this on this cut line here, it says process part 1, opens a curly brace, and then we've got input equals, and then the input that we're getting from that file. Now, maybe we don't want that to always happen, so we can do things like skip input. And now we've got info process part 1, our function, is still being traced as a span, day 20, and then our logout. So we still know that we're in the function process part 1, which is additional information we didn't have before, but now we've skipped outputting the input file because maybe we don't really need that. With the tracing crate, this gets as customizable as you need it to be, is the way that I'll put it. You can output to a JSON format. You can output your values that you're passing in as nested JSON inside of that JSON format, and so on and so forth. So I skipped the input because I didn't want to deal with it. We can throw this instrument macro, which opens a span on any of our functions. So if I wanted to do something in here like print out the numbers, I could do that. But notice that there is an error here because Rust is such a nice typed language. It says the trait value is not implemented for vec of whatever, and the macros that we get from tracing have additional functionality. So if we want to debug that out as a debugged value, like a debug formatted value, we can use the question mark here on numbers. And then when we go through part 1 numbers, we get the input again as the argument that's getting passed in, as well as the numbers value equals, and then the debug formatted value of that vec. And this is all checked. So if I put input, it works. If I put something else in here, it'll say, hey, this doesn't exist. This isn't a parameter to this function, which is really nice. So we'll skip the input because we don't need it. I don't really need the numbers to get printed out for me, I don't think. But notice now that we've got process part 1 numbers in our list, as well as process part 1 with our output. So we didn't set up our log level here, so there is a default, and that default clearly puts out the info stuff. If we did something like warn, that shows up as warn. There's also error, which shows up as bright red with an error. There's debug, which is actually ignored, you'll see, because we aren't logging out with that level of verbosity. And in that way, you can kind of like select what you're going to look at. So in this case, I'll leave it because we're going to explore more tracing stuff. We've got process part 1 numbers. We don't really have any additional functions here, but we'll roll tracing forward for the rest of the problems for the week. So now we need to figure out if what we're doing is correct. So I think we want to do like an info for state, and then at the end of every iteration, another info for state. And this just prints us out all of those values. So now we see state equals whatever in process part 1. And you can see that it gets printed out for every iteration. And let's see, 1, 2, -3, yada, yada. So 2, 1, -3 is the next one. 2, 1, -3, 3, 2, 0. 2, 1, -3, 3, 2, 0. And then where's 4? Are we not inserting? Let's see. So the result of state.insert is unit. So maybe we do an info on new index. And you'll see the issue here is that this actually doesn't take function calls. So like if you call a function similar to the way that you would do so in like a format or a print line, this would need to get formatted out like that. So if it's not a variable name, if you're calling a function on something, you can either do it outside of the info, or you can do it just like you would in a print line or a format. And this is just the default output. There's also like a super fancy output as well as the JSON output. So since the values here are always going to be correct, maybe what we do is state.iter.map v.1, just to show all of the output in a little bit of a more readable way. So this is new index. And 4 just gets lopped off, doesn't it? Everything else gets reinserted, but if we get, a value that is too long? So let's bring value in and let's do moving. We'll just have value sitting here. So notable that any of the values that are just variable names that you want to print out have to come before the formatting string, whereas any values that you would pass into that formatting string would come after. So moving value equals 1, 1, moving value equals 2, moving value equals -3, 1, 2, -3, -2, 0. Did I mess up the parsing? I messed up the parsing when I did this, didn't I? Because it's not pulling in 4 anymore. Haha. I should have read the numbers. 1, 2, -3, 3, -2, 0. That's 6. So this terminated iterator doesn't really work. So it's either alt, line ending. I think there's an EOF, so non-combinator EOF, which would be end of file. So we get 4 now because we had to include the end of file for this terminated. Usually not an issue, but because we went with the iterator and we went with the terminated instead of a separated list 1, then we got to deal with this. So now we can see from our tracing that we've got 1, 2, -3, 3, -2, 0, 4, and then We have 9, so we get 3, 3, and 3. So 2, 1, negative 3, 3, negative 2, 2, 1, negative 3, 3, negative 2, 0, 4. And then 1, negative 3, 2, 1, negative 3, 2, 3, negative 2, 0, 4. That's good. 1, 2, 3, negative 2, negative 3. 1, 2, this is wrong. 1, 2, 3. So the first negative one is wrong, which means that I think my guess earlier was correct in that this new index here, right, is going to be, so here I've changed the info to be the new index and then the state.length. So we get moving value negative 3, and then we get the length is 6 because we are post remove. So if the new index is negative 2, that would put it at 2 right now, but it should be at 0, 1, 2, 3, 4. It should be at 4. So it should be only if this is negative though. If new index.signum equals negative 1, then we do one thing, else we do another. And this is going to be, this doesn't need to be absolute value because it's always positive. And this is going to be, so if we're cycling, what's the more obvious way to do, or not the more obvious, but the mod way to do this? It's not it, we'll just get state at 1000 mod state.length. Is that right? We've got some issues. These are all .1. We've got negative 2, 3, and 0. So let's see. 1000, the 1000th number after 0. Then the groove coordinates can be found by looking at the 1000th, 2000th, and 3000th numbers after 0. Ugh. Why is it after 0? Is there only 1 0 in this whole thing? What's special about 0? Do they even tell us? They don't even tell us that 0 is going to be guaranteed unique, right? So in our puzzle input, there's 5,000 numbers. Is there only 1 0? According to NewShell anyway. If we take the input, I pulled it in like it was a CSV, where negative 6020, which is the column name for all the values, equals 0. We only get one of them. So I'm assuming we only have one. So I guess we just find 0 and find the index of 0 and then do this. State.iter.position v.1 equals 0. 0 position equals this. It's an option. Unwrap it because it always has to work. So it's what? These plus 0 position, which gives us a passing test, which is very cool. So now we could do like cargo run bin part 1. And we get all of this, tons of output, but included in tracing, we can actually just not output that. So if we do rest log equals empty string, for example, and we run part 1, then we don't get any of that output at all. This is attempt to add with overflow, source lib.rs52. This is going to be the issue of each of the numbers being bigger than the actual index that we have. Wait, attempt to add with overflow? Let's debug that out. So we can still use debug, right? We see all of this stuff. So if we have a quick thing that we want to drop in, we can debug it with dbg, which doesn't get sent through the tracing stuff. So I really only want to print out when we hit this if, but if we hit the if, then we have a problem, right? So if I debug index and I debug current 1 and we run this, then we see that current 1 as usize is what looks like a max value. So current 1 can be negative if it gets to here, which is weird because if new index.signum is being checked right here, so I'm going to bring our logging back, and you can see that we get a lot of this like whole set of numbers because the actual list of numbers is entirely too big to print out, really. It's a 5,000 list of numbers. Day 20, moving value 12. So if we just do current value 1, what do we get? We get negative 12. How did we get here for negative 12? Because if new index.signum is never negative 1, oh, okay. So that's not possible anyway. If we add the index to the current value and the current value is negative, so that should never happen. So this and that not equals, and then we get rid of these debugs because we don't need them anymore. Attempt to add with overflow on 53. That's the same one, which is really weird. Okay, maybe we do need the debugs back here. It's still negative 12. If new index.signum is not equal to negative 1, signum of negative 12 is negative 1, right? Oh, that's because I didn't change it. Current.1.signum is what we needed. Oops, my bad. So now this is running and just absolutely dumping output to the console, and I don't want to see any of it, so I just get rid of it. Of course, the debugs don't respond to the tracing crate, so that's that. This is a number that we might have an answer. I hope it is. That's not the right answer. Our tests still pass, right? Yeah, tests pass. This is always the most disappointing part of Advent of Code, when you have an answer that passes your tests, and the actual input that you're given enforces additional constraints on the problem that are not described. So when we are doing our finds, our position, right, we are looking for the IDs, except for when we're looking for 0. That's good. So maybe we start off with, I feel like I'm doing too much here. I think this is an indication that my modulo is wrong. It didn't tell me whether I was too low or too high, so I'm assuming I'm just way off. And I just chose, like, I'm just getting the wrong numbers. So this modulo, where are we? This modulo to create the new index. What's the behavior of this when it's negative numbers? So in Rust, percent is remainder, which is what we want it to be. So that's why I'm on the standard ops rem page. If we do this, rem Euclid, is that right? That gives us 3. I think that's the answer. I think we're supposed to be doing rem Euclid, not rem. 10, I32. Okay, yeah, I think rem Euclid is what we want. I can find this. Overflowing rem. It's in here somewhere. Checked rem Euclid. Rem Euclid. Okay. Calculates the least non-negative remainder of self, as opposed to rem, which for some reason is different. And I don't quite understand the difference. So if you know the difference between rem and rem Euclid, let me know. I just happened to remember that there were other rems and I took a chance on it. But if you've been watching this video, you know that modulo math is not my strong suit. Where's our thing? This rem Euclid list. Then we can get rid of the absolute value, and then we run into the same problem. Moving value 1, right? Index, which is 0, plus current. Are we supposed to start off with 1? Yeah, 1 moves between 2 and -3. So the index is 0, right? And the current dot 1 is 1. So added is 1. 1 rem Euclid 7, I think, is just the value we need. We don't need to do that subtraction anymore. So moving value 1, new index 1, 2, 1, -3. And then I think we end up with, what is this? -2. I think we still end up with that -2 problem that we had earlier, right? 1, 2, -2. Let's get rid of this. 1, 2, -2, -3, 0, 3, 4. That's where we are. And then the -2 is supposed to cycle around. I really don't understand why it's supposed to cycle around there. But we end up with -2, 1, 2, 4, 0, -2, 1, 2. Yeah, I don't know why this is hanging off the end like that. So 0 has to be pushed to the end. So hopefully 0 will never be in the 0 position. And then if I remember correctly, the 4 runs into the same problem in the other direction, right? Actually, I don't think it does. I think it slots right into where it's supposed to be. The -2 just needs to be the other way. So if new index is 0, we do that special case. Otherwise, we do the regular case. We don't want it to be 6. We want it to be list length -1 from earlier. So that wraps the 2 around for us. I don't know why 0 is now the end. I don't know why more accurately, I don't know why the test input requires 0 to be the end. I feel like when we move 4, we go through this 4, 1, 2, 4. So it should be 1, 2, 0, 1, 2, 0, -3, 1, 2, 0. That's not right. Hang on. 0 isn't in the right spot. Let's do 1, 2, -2, -3. Let's see. 1, 2, -2, 0. 0 never moves. 1, 2, 0. 1, 2, -2, 0. 1, 2, -2. Okay, so the 0 is in the wrong spot. 1, 2, 0, -3. We're never at 1, 2, 0, -3. 1, 2, 3, -2. 1, 2, 3, -2. That's not right. We're all the way back up here. 1, -3, 2, 3. 1, -3, 2, 3. -2, 0, 4. So this is our most recent correct value right here. Then we move -3. 1, -3, 2, 3. -204. So this is accurate. And then -3, 1, 2, 3, -2, 1, 1, 2, 3, -2, 0, -3, 4. So it needs to go further because it looped around the other way. And new index is 5. So if the moving value is negative, do we always have to do this? -3 is the first negative value, right? Yeah. So maybe it's not 0. Maybe it's... The 0 is still a special case, though, because if we go to 0, we have to put it on the end. Do something silly like that. I don't know why that has to happen, though. That fixes it, but I don't know why that has to happen. That doesn't fix the 0 problem, does it? Yeah, it does fix the 0 problem. So I don't understand why this works, but it does. So index as I32 plus current 1. And then if the value is negative, we subtract an additional 1 from it. Whereas if it's positive, we don't do anything. And we end up with 1, 2, 4, -3, 0. So 1, 2, 4, -3. This is wrong though. I'm getting the right test answer with the wrong input. 4 still needs to be one further. This isn't just a universal thing, right? It's not just a -1, 1, 4, 2. 4. So let's look at 4 at index 5, right? 0, 1, 2, 3, 4, 5. New index 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 1. So 1, 2, 3, 0, 1, 2. So it replaces 2? Is that the issue? Is it because I'm modifying the length of the list? Is that what it is? But the other ones are fine, right? Moving value 2, index currently 0, new index is 2. So it goes 0, 1, 2. Because everything shifted left 1, do we just need to do the remove afterwards? Would that clean everything up? So we do this, right? And then the mutation modifies the list. That doesn't help me actually. Am I supposed to do the math after? So I add them, and then is it not list length? Is it state that length? Is that my issue? Am I just being silly? Ooh, okay, I think that was it. That's really not fun, but it works. And we get a completely different answer for the big one. So hopefully it was just that off by 1 error, and it was just that off by 1 error. I finally got my modulo math correct. Holy, that was an adventure. I don't know why I got so tripped up on removing this and the list length changing. Okay, so process part 1, numbers, state. We're using tracing for every ID and value in the numbers list. We're logging out moving with the value that we're moving. We do let sum to get the thing from the position. We could also just unwrap. I'm just panicking here, so let's just unwrap because this always has to work anyway. So we don't need the let syntax here. So, or the let else syntax. So let index equals state iter position to find the position of the one that we need to remove. We remove it. That gives us current, which is the item from that position. We add the index that it's currently at or was at with the value that we removed. The new index is calculated using rem Euclid, not just the modulo operator. Modulo operator is the wrong operator because we have to deal with the negative numbers. So the two numbers added together, rem Euclid with the length of the state array after the removal, which feels weird, but that's the way it works. Then we just insert that into the new index where it should be, and we're done. And we've got a bunch of logs in here. The way that we get the answer is taking the 0 position or finding the 0 position index in this array, and then doing a modulo operator because everything's going to be positive, so we can actually use modulo. The 0 position plus 1,000 modulo with the length of the array. And then because those values are tuples, we do .1, and that gives us A, B, and C, which we can then add together. So that's part 1. The Grove coordinate values seem nonsensical. They ain't that true. While you ponder the mysteries of elf encryption, you suddenly remember the rest of the decryption routine you overheard back at camp. First, you need to apply the decryption key, whatever this is. Multiply each number by the decryption key before you begin. This will produce the actual list of elements. Okay. Second, you need to mix the list of numbers 10 times, not just one. The order in which the numbers are mixed does not change during mixing. The numbers are still moved in the order they appeared in the original pre-mixed list, so we get to keep our ordering using the same example as above, yada yada. The coordinates can still be found in the same way. Thousandth number, 2 and 3,000th, add them together after they've been mixed. So we need to multiply everything by that number. Let's copy and paste this because we're just going to modify our part 1 code. The number that we need to multiply by is this. So numbers equals numbers dot iter. I guess we could iter mute here. That would be fun too. Let's do an iter mute. That means this needs to be mutable. So if we do an iter mute, we don't need to modify numbers. We just do numbers iter mute for each, and then we have the thing that we apply to each value, which I like quite a bit. And all we're doing is multiplying. So times equals the number that we were given. What is going on there? There we go. So we'll run the test. We need to enable our second part. We need to go grab the actual answer to the second part, which is this, which goes here. We don't need to toString that. And then I'll ignore part 1 for now because we have all of our subscriber. So this instantiates a global subscriber. Not really going to go over what that means. I'm just going to let you know that you can't do it twice. So I'm going to ignore this test and run this test. So attempt to multiply with overflow. I assume that means that we need I64s, which would make sense to me. I'm going to go ahead and assume that using I64s doesn't change anything. So we have numbers here. We have to iterate over them 10 times. So the question is, how do we do this 10 times? I think that the easiest way would be 0.10 and just putting another loop on the outside of this. We don't ever use that value, but we do pass our tests now, which is wonderful. Sometimes just adding the simple cargo run bin part 2. This, of course, is logging out everything, so we don't want that to happen. So we set the environment variable to empty, and we just run it, and then we get a value, and that gives us a gold star. So because we did all the mod math in the first one, instead of taking the naive approach, we front-loaded all of the pain of doing so. And then when we had to do part 2, all we had to do was modify the numbers by multiplying each by this, and then iterate over this for loop that was doing all of the interesting moving of the numbers 10 times. And then all of the other logics did the same. Huzzah. So we got to look at tracing today. We spent a little bit too much time doing modulo math because I forgot about Rem Euclid, but otherwise pretty happy with today. We'll roll the tracing stuff forward and we'll start using tracing more. And I don't know if there's enough to go over here for criterion or DAT, which are two things that I still want to get through. Maybe could at least read them out. The issue so far has been that whenever we run into a performance issue, it's always the kind of this will not run in an acceptable amount of time, or quite often it is. So when we get it to run, we could keep optimizing it, but we've spent a bunch of time doing the optimization already, which isn't really like criterion useful. And then for DAT, it's a heap memory profiler. So it would tell us how much space we're using, but we aren't really doing anything here that allocates space in any interesting way. So I don't know that it's easy to show off in this example. So I think we'll push those off till tomorrow, and we've done tracing now. So I hope you enjoyed the video and have a great rest of your day.